Welcome to this Coach Store. Today we're going to start talking about integration. Before we do that, let's do an overview of calculus. Now, there are two main ideas in calculus. There is derivatives and integrals. We've been talking about derivatives. We can think of derivatives if I have the graph of a function, y equals f of x here, shown in blue, and I take some point, x equals a here, and I look at that point on the curve, then I can draw a tangent line that intersects that blue curve at just one point locally. And that slope of that green line, that tangent line, equals the derivative at a. And so we can think of the derivative as the slope of the tangent line. And more importantly, though, when we get into applications, we really think of derivative as the rate of change. And that allows us then to apply calculus and derivatives to lots of examples in science, technology, engineering, and mathematics. Now we're going to begin talking about integrals, the second main idea of calculus. And again, we can start with the graph of a curve here, y equals f of x. And this time we're going to have 2 points we're going to look at. Let's say a point x equals a here and x equals b. And what we're going to get now is that we're going to look at the area under the graph, but above the x-axis. And we're going to look at that area, and that area equals the integral. So we're going to be interested in that area. Now, this may not seem real exciting to you, but to me, it is really important because what's happening here are two things. First of all, we are going to get some applications of the integrals, of finding the areas under the curves, and we're going to be able to connect derivatives with integrals. So we're going to talk more about that connection later on, and that's going to be the fundamental theorem of calculus. And in my mind, that's the culmination, the highlight of this course, is this connection between derivatives and integrals. And we're also going to talk about some of the applications of integrals as we go further on. But for now, we just want to lay the foundation of it. So you'll have to hold on to that until we get a little bit further on. Let's look at an example using Desmos here. So I'm going to have this function f of x equals 1 plus x squared. The graph of that looks like this black line here, this parabola that's shifted up one space. All right. And I'm going to be looking at the area under this curve from x equals 0 to x equals 1. All right. That's what I want to find. I want to find out what that area is. How am I going to do that? I'm going to do that by putting a rectangle underneath this to approximate it. So let's put one rectangle there. So there's a rectangle. It's between x equals 0 and 1, and it's below the graph of the curve and above the x-axis. What's the area of that rectangle? Well, it has a base of 1 and a height of 1, and so the area is 1. To figure out the height, what I've done is I've taken the leftmost x value of the rectangle, and I've plugged that value into my curve to find out where that x value would hit the curve there. So the x value is 0. Again, my function is f of x equals 1 plus x squared. So when x is 0, that gives me a value of 1, and that gives me this point right up here, which has a height of 1 right there. Now, what's wrong with this is that I don't get the correct exact value under the curve. There's all this white space that's missing here. So in order to get a better approximation, we're going to increase the number of rectangles. We're going to go to 2 rectangles. Now this, you can tell, is going to give me a better approximation because we have this new green area that's added in that's different than the previous one. Remember, the previous one had this 1 by 1 rectangle, but now we have these 2 rectangles. When I add them together, I have more green area under the curve and less white area that is missing. That white area is smaller. Now, how do I figure out the value of these rectangles? Well, now the base has decreased. Each one is now a half. The base of each rectangle is a half. And the height is the same idea. I take the leftmost point, that x value there, and then I plug it back into the original function, 1 plus x squared, and that tells me what the height is. So when x is 0 on the left rectangle, x is 0, I get it goes up and hits the function at the value of 1. When x is a half, that's the left part of the right rectangle. When I put in a half here, then I get a value of 1.25 for the height of the rectangle. And when I add those together, I now have this value of 1.125 for the sum of the areas of the two rectangles. And that's a better approximation. Remember the previous one, when we did one rectangle, we had a value of 1. Now we have 1.125, and that's getting closer. Well, I can keep doing this. I can go up to 4 rectangles. And if I do that, now the base of each rectangle is a fourth. And the height, again, I will take the left x value in each rectangle, plug it into my function, 1 plus x squared, and that will give me the height value. So at each of these, I get the height value, and I can then use those to figure out the area of each rectangle. And when I do that, then I get that the total area of the sum of the areas of the 4 rectangles is larger than the previous one. And we can see by the graph that is getting closer to the actual value because I'm having less white space under the curve, but above the green rectangles. And I can keep doing this. And as I do this, I get a better and better approximation. All right. And this is where the calculus comes in, because what we've done now is we've taken the limits here. And as we take the idea of limits, which is something we can talk about now with calculus, then we can get the exact value. You weren't able to do this before calculus. You could still do these rectangles. It'd be tedious to figure out the values, but you could figure them out. But you wouldn't know the exact value as you did it in limits. And that's where the limits come in, and that allows us then to do calculus. Now, another thing that we can do here, in each of these examples, we took the rectangle, we used these rectangles that were underneath the curve. And the way that would happen is we took the left x value for each of the rectangles. Now, let's change it and do the right x value. So my left, now I have 2 rectangles. My left rectangle, instead of using the left x value, I'm going to use the right x value to go all the way up to the curve. So in this case, for the left rectangle, I'm going to use the value x equals a half, and I plug that into my function 1 plus x squared, and I get this height value 1.25. So this left rectangle now has a base of a half and a height of 1.25. The right rectangle now has a base of a half and a height of 2, because I'm putting in x equals 1, the right side of it. And that's now going to give me, when I put that into my function 1 plus x squared, it gives me a height of 2. And so when I add those up, those 2 areas, I get 1.625 as the area for the 2 rectangles. And we see that that's a bit more than what we want, because there's green area above the curve. But again, like last time, we can increase the number of rectangles. And as we increase the number of rectangles, we get a better and better approximation. All right. And again, then what we can do is we can take the limit as n goes to infinity, and we get the exact value here. And in this case, what's going to happen is my exact value is going to be 1.3 with a line over it, 1.3333, or 4/3. And we'll talk later about how we actually find out that exact value. But for now, I want you to see that the integral is thought about as the area under the curve. So let's go back to my iPad here, and let's talk a little bit more about this. What I'm going to be doing is I'm going to have the graph of a function, y equals f of x. I'm going to have an x value called a and an x value called b. And I want to find the area underneath the blue curve there, y equals f of x, above the x-axis, which is the black line, and between the 2 red lines. And what I'm going to do is create a bunch of rectangles. And I'm going to use these rectangles to approximate the area of the curve. All right. So we're going to let n equal the number of rectangles, and we're going to call this delta x. That little triangle shape is the Greek letter, it's the capital Greek letter delta. So Delta Airlines, that's where they get they're from. And it's delta is the equivalent of the letter D in Greek. Greek calls it delta, we call it letter D. And that's going to equal then b minus a over n. That's going to be equal to the length of each rectangle. All right, so for example, like we had before, if my function is 1 plus x squared, and I have a to b going from 0 to 1, then this is going to give me that b minus a over n is 1 minus 0 over n, which is 1 over n. So delta x is going to equal 1 over n. And in the case I had, let's say I had 4 rectangles, that means n equals 4. Then the length of each rectangle was 1/4. Okay. F of xi is going to equal the height of each rectangle. And it's going to change for each of the rectangles. And you can see that in this picture here, the height is going to change when we do this. Okay. We're going to call x sub I to equal a plus I delta x. And this is, yeah, the x sub I is going to be on the base of the rectangle. And so this is going to give me, that will give me my x value. And this is going to signify the right endpoint of each rectangle. Remember how we talked about that in my function here, y equals f of x, and I got my points here, a and b, x equals a, x equals b. As I draw rectangles inside here, I can either take the left-hand side or the right-hand side. If I take the right-hand side, I take the right value there, and that gives me my rectangle. Here we're taking the right endpoints because I'm taking for each rectangle, I'm using the x value on the right side of it, and then that going up to the curve, that gives me the height value there. All right, then what we're going to get then is the definition of the integral, and it's going to be this squiggly, almost like an S there, from a to b of f of x dx. That's the integral, and it's going to equal the limit as n goes to infinity of the sum I equals 1 to n of f of x sub I delta x. All right, so what's happening here with these terms here? Okay, this part is what's called the integral. All right, we've got my squiggly thing out front is the integral sign. This is the integral sign, and it kind of looks like an S, which represents then like the word sum, S-U-M, like summing up the rectangles together. All right, these A and B, these are called the limits of integration. And those are the numbers, the x values that you're doing the integral from. All right, so in my previous example, I had the integral from 0 to 1 of 1 plus x squared dx. All right, this was b equals 0, and this was b equals 1, and this was my function, okay, which is called the integrand. And so that gave me the image that we had where I had this curve. So here's the curve y equals 1 plus x squared, and we're going from x equals 0 to x equals 1, and we're trying to find the area underneath that curve there. And this area is represented by the integral from 0 to 1 of 1 plus x squared dx. Okay, now when we talk about this, we say this integral from a to b of f of x dx is going to equal the limit, n goes to infinity, of the sum I equals 1 to n of f of x of I delta x. So what's happening here on the right-hand side? Well, this represents the area of a rectangle, okay, because here is the base and this is the height of the rectangle. So when I multiply the base times the height, I get the area of a rectangle. So I get one rectangle there. Then this summation here is adding all the areas of the rectangles together. That's what the summation sign does. Okay, and the last thing is we do the limit here. We take the limit as n goes to infinity. So we get more and more rectangles there. And in the limit, then we fill in all the area underneath the curve above the x-axis. Okay, so that's how the definition of the integral means. Okay, so a few other things I want to just say here. This summation I equals 1 to n of f of x sub I delta x, which again, that is adding up all the rectangles together. We have n rectangles. We have n of them because of this. We're going from 1 to n, so we have n rectangles, and these are all this f of x of I times delta x. That's the area of one of the rectangles. And then the summation in front of it means I'm adding all those areas together. So I have the area of n rectangles there. This expression is called the Riemann sum. And that's in honor of a mathematician named Riemann, a German mathematician. Okay, so use this idea to look at some example problems. So you're supposed to estimate the area under the graph shown in this figure below, where x is going from 0 to 2, and you're using rectangles with the same base length. And you're supposed to use 2 rectangles and use the left endpoints. What is the estimate for the area under the curve doing that? All right, so here you can see reproduction of what the graph we had there. And we were supposed to use 2 rectangles here, and we're going to use the left endpoints. All right, so I'm going to use 2 rectangles. How do I figure out the height of these rectangles? Well, it said to use the left endpoint. So for the left rectangle, I'm going to use this point. That means I go all the way up to the curve here, and there is my first rectangle. What's the area of that? Well, it's base times height. The base is 1, and the height is 1. Okay, here's the base. Base equals 1, and this height is 1. For the second rectangle, the one on the right, I'm going to use this green color here, and the rectangle is going to look like this. All right, the base is 1 also, and the height now is 3/4. Comes from this value right there. So this area here equals base times height, and it equals 1 times 3/4. So the total area, the sum of the areas is going to equal 1, because that's what this is, plus 3/4, okay, which then I could write as 7/4. All right, that's using the right endpoints. Now the problem asked, what if you used, that's using the left endpoints. So that's using left endpoints. Now let's do the same thing using right endpoints. Okay, now I'm going to use right endpoints. Here's a graph of it. So I'm going to have 2 rectangles again. So I'll have 1 rectangle here and in blue and 1 in green. But now I'm going to do the left endpoints. So for the blue one, I'm going to use this point, and I'm going to go up here, and that's going to be my rectangle. The base is 1, and the height is 3/4, which comes from this value right there. For the second one, I've got a base of 1, and the height is right here, and that comes this value here. The height is 0. So the areas are for the left rectangle. So I'm going to get left rectangle area equals base times height, which is 1 times 3/4, which is 3/4. For the right rectangle, the area is base times height, which is 1 times 0, which is 0. So the approximate area using 2 rectangles with right endpoints is 3/4 0, which is 3/4. Okay, let's get another example. All right, in this example, my function is not given as a graph, but is given as a table. And it says, as gasoline is pumped into a car, a measurement is taken every half second to capture the rate at which the gasoline is flowing into the car. Given the following measurements over a 3-second time interval, use right endpoints rule to estimate the amount of gasoline pumped into the car during the 3-second interval. All right, so here's the reproduction of the table, and we've got the right endpoint rule. So each connecting block there represents a rectangle. So my base is represented by here. That's my base. Okay, so base is a half. And then my height is going to be using the right point. So this is going to represent my height for the first rectangle. So in that first rectangle, so we'll call that rectangle 1, I got base times height, which is going to be a half times 3. For the second rectangle, I'm going to mark that in green. It's going to be here, this rectangle. Its base is also a half. I have 1 minus 0.5, and this is the height. So its base times height is going to equal a half times 3. And now I can keep doing this for each of these. I have third rectangle in purple, rectangle 3, then its area is going to be base times height, which is going to be a half, because it's going to be 1.5 times minus 1 times the height of 4. There's the height. And then I just keep doing the same pattern here. Rectangle 4 is base times height. It's going to be a half times 4, using that one. And let's see, I'll use red again here. The fifth rectangle is going to be this one, where my height now is 2. So I get base times height is a half, height is 2. And then the last one, I'll use in blue here, this one, and its base is a half and its height is 3. Okay, so just doing these all together, I get 3 halves, 3 halves, I get 2, here I get 2, here I get 1, and here I get 3 halves. And adding these all together, because we're just adding all the rectangles together, I get 3 halves plus 3 halves plus 2 plus 2 plus 1 plus 3 halves. And when I do that, I will end up with 19 halves. That's another example of how to do these integral problems as an approximation. Let's go back to the definition of the integral. So the definition of the integral, which was the integral from a to b of f of x dx, can be written as the limit, as n goes to infinity, of the sum I equals 1 to n of f of x of I delta x, where we remember that delta x equals b minus a over n, and x of I equals a plus I delta x. Okay, there's the definition. Now we're going to use that then to go back and forth between Riemann sums and integrals. So here's an example. Express the integral from 0 to 5 of 1 plus 2x cubed dx as a limit of Riemann sums. Okay, we're using that definition of the derivative here. So we're given 0 to 5 of 1 plus 2x cubed dx. So this is telling me that my function, my integrand, is 1 plus 2x cubed. My a is 0, and my b is 5. All right. So then I use the fact that delta x equals b minus a over n. And so I'm going to get 5 minus 0 over n, or 5 over n, is delta x. X of I equals a plus I delta x. So this is going to equal 0 plus I, and delta x was 5 over n. We saw there, so we get 5i over n. That's delta x. Okay, finally I can do fx of I. So this means I'm going to take my f function, which is up here, and I'm going to do 1 plus 2. And instead of putting x in there, I'm now going to put in x of I. So that's going to be 5i over n cubed. All right, so then using the definition, the integral from a to b of f of x dx equals the limit, as n goes to infinity, of the sum I equals 1 to n of f of x of I delta x. So in this one, we're going to have the limit. So in this one, yeah, we have 0 to 5 of 1 plus 2x cubed dx. That's going to equal, the limit as n goes to infinity of the sum I equals 1 to n. And now I'm going to put in my f of x of I. So that's going to go in there. So I'm going to have 1 plus 2, 5i over n cubed. And then it's all times this delta x. And delta x was this. So I'm going to put this in right here and get 5 over n. So there is my answer. And that then shows the connection between the integral and the limit of the Riemann sums. All right, let's do one in the opposite direction here. So we're going to express the limit of a Riemann sum. So the limit as n goes to infinity of the sum I equals 1 to n of 1 over n times 1 over 1 plus I over n squared as a definite integral. Now I put the word definite there. Definite integral just means that I have my a and b values are given to me. Okay. Don't worry about that right now. We'll talk more about that later. So again, I'm going to use my definition. So that one, if I write it going the other direction, the limit as n goes to infinity of the sum I equals 1 to n of f of x sub I delta x equals the integral from a to b of f of x dx, where we remember then that we have delta x equals b minus a over n, and x sub I equals a plus I delta x. And just to reemphasize that when I do a plus I delta x, that means I'm doing the right endpoints. I'm doing the right endpoint way of doing it using this definition. Okay, so given this problem here, so first thing I will need to do is figure out which one of these terms is a delta x and which one is the f of x sub I. So I've got the 1 over x, and I've got the 1 over the 1 plus parentheses I over n squared. One of these is delta x and one of these is f of x sub I. Well, the f of x sub I is going to be this one because there's the term where I have an I in it. I don't have an I in the red circled 1 over n. There's only an I in the green circled one. So that has to be my f of I. Delta x has to be the 1 over n there. It doesn't matter that I've switched the order, that the 1 over n comes first in the given problem, because it's a multiplication. It doesn't matter which order they come in. But what's important is to realize which one has the i's in it, and the term that has the I in it is going to become my f of x sub I, and the other one's going to be the delta x. Okay, so know then, given that delta x is 1 over n, but delta x from up here is b minus a. So what does that tell me? That tells me b minus a has to equal 1, right? Because I have the b minus a on the top here, and I have a 1 on the top here. Okay, so I have b minus a equals 1. And then what else do I know? I also know from the green part that the f of x sub I equals 1 over 1 plus parentheses I over n quantity squared. All right, this suggests to me that my f of x is going to be 1 over 1 plus x squared. All right, and then this part inside here is my x sub I part, because then you can see that what I circled in purple there is x sub I, and that means what I have here is 1 over 1 plus x sub I squared. That matches what I have for my green part function here, f of x equaling 1 over 1 plus x squared. And since x sub I is what we circled here, 1 over n, and remember x sub I equals a plus I delta x, all right? But we also know that delta x is 1 over n. So we have x sub I equals a plus I over n, all right? But we said x sub I equals I over n. So if these two are the same, this means a has to equal 0. So that then gives me a bunch of things. A equals 0. Then we know from up here in blue that b minus a equals 1. So that means b has to equal 1. So I have b equals 1, a equals 0, and f of x is 1 over 1 plus x squared. So then I've got that my limit as n goes to infinity of the sum I equals 1 to n of 1 over n times 1 over 1 plus I over n squared, the original problem, is equal to the integral from a to b of f of x dx. And so now when I substitute those values in, a is 0, b was 1, and f of x is 1 over 1 plus x squared dx. And so that becomes my answer there. All right. There's some more examples in my lecture notes here on these, but let me give you one other example here. We've talked about this case that the integral represents the area under the curve and above the x-axis. But what happens if the curve goes below the x-axis? All right, what if I have my graph of my function looks like this? All right, we're going to say here's x of a and here is x of b. So we've got these various areas. Some of it is below the x-axis there. So we're going to call this area, this positive area A1, this positive area A2, and this positive area A3. And what's going to happen now, the integral from a to b, okay, remember a is left, b is the right point there, of the function f of x, and my curve here is y equals f of x, is going to equal the area of A1 minus the area of A2 plus the area of A3. So if an area goes below the x-axis, then we subtract the area from the amount we have. All right, I think that's good for now. Hope that helps. Thanks.